In this study, we present the experimental and theoretical investigation of the high-field phase diagram of the chiral-lattice antiferromagnet senior, TiO, Cu4, PO4, 4. The research employs ultrasound, dielectric, and magnetocaloric effect measurements, complemented by cluster mean-field theory. The experimental BT phase diagram reveals two new phase transitions at high fields, which were not observed in previous magnetization experiments. These transitions are attributed to strong magneto-elastic coupling and the chiral-twist effect of Cu4O12 cupola units. Theoretical calculations based on the cluster mean-field approach are in good agreement with the experimental results, suggesting that SRTCPO is a unique quasi-wo-dimensional spin system with competing exchange interactions and chirality, leading to a rich phase diagram. The study provides insights into the exotic properties of chiral magnets and the potential for novel exotic states of matter. In this study, the authors present a theoretical and experimental analysis of the magnetic properties of SRTCPO, a spin-half-a-square cupola compound, focusing on its magnetic phase diagram and the spin-lattice coupling. The effective spin model for the Cu2+ cations is introduced, which includes 4 dominant antiferromagnetic exchange interactions, a Dzielinski-Moria interaction, and a Zeeman coupling. The Hamiltonian is solved using the cluster mean-field (CMF) theory, which accounts for quantum fluctuations within each cupola and uses mean-field approximation for weaker intercupola interactions. The temperature dependence of the elastic constants at zero field shows anomalies at the ordering temperature, Tn equals 6.3 K, indicating long-range magnetic ordering. The C66 mode exhibits the largest softening, reflecting strong spin-lattice coupling with the AB plane shear strain. The other acoustic modes show weaker elastic anomalies, consistent with two-dimensional spin systems where in-plane strains generally exhibit larger spin-lattice coupling than out-of-plane strains. The C66 mode at zero field also displays a broad minimum at around 5 K, which gradually disappears with an applied magnetic field. This anomaly is linked to a hump in the specific heat divided by temperature, observed around 5.5 K, suggesting a possible role of magnetic domains. The authors discuss the potential impact of antiferroquadrupolar magnetic order and domain walls on the observed elastic anomalies, particularly in the context of similar phenomena in other materials like Cu4 and alpha-Nav2O5. The magnetic order in SRTCPO is characterized by antiferroquadrupolar type, Qx2y2, where magnetic quadrupoles align in a ferroic manner within the two-dimensional magnetic layer but antiferroically along the axis. The existence of two domains with opposite magnetic quadrupoles could contribute to the observed anomalies in the elastic constants and specific heat. The research paper presents an investigation of the magnetic field dependence of acoustic properties and the magnetocaloric effect, MCE, in a frustrated magnet. The study focuses on the magnetic field-induced phase transitions and their corresponding elastic and dielectric anomalies. The acoustic properties exhibit clear discontinuities and hysteresis loops in the elastic constants, C66, C11, and C44, for magnetic fields along the 001, 100, and 110 axes. These features are attributed to field-induced phase transitions, which are also observed in magnetization measurements. The C66 mode shows a complex hysteresis loop, indicating strong in-plane spin-strain correlations. The acoustic attenuation becomes minimal at fields between B001, C1 and B001, C2, suggesting a thermodynamically stable phase. The dielectric constant, epsilon 100, exhibits broad peak structures and hysteresis for magnetic fields along the 001 and 100 axes, respectively. The increase in epsilon 100 is attributed to the exchange striction mechanism, where the induced polarization is proportional to CSJ. The MCE data reveal reversible and irreversible temperature changes depending on the initial temperature, T0, and magnetic field direction. For T0 greater than 5 K, the MCE curves are reversible, indicating adiabatic conditions. In contrast, for T0 less than 5 K, the MCE curves show irreversible behavior with hysteresis. The MCE curves exhibit kinks around the saturation field, and the temperature decrease indicates an increase in magnetic entropy towards the field-induced transition. Theoretical phase diagrams are presented for a chiral twist angle of phi equals 1 degree, which show that all phases seen for phi equals 0 degrees are also stable for phi equals 1 degree. The obtained phase diagrams are similar for the field directions B parallel, 001, and B parallel, 110, while the high field Y phase is largely affected by the twist angle. The study provides a comprehensive understanding of the interplay between magnetic fields, acoustic properties, and the MCE in frustrated magnets, highlighting the importance of considering the chiral twist angle in theoretical models. Future work is suggested to investigate the phase transitions in static magnetic fields and to explore the observed anomalies in more detail. The research paper discusses the magnetic field-induced phase transitions in a specific material. It presents theoretical and experimental results on the entropy landscape and elastic anomalies under different magnetic field directions. The entropy calculations and MCE results agree well with the theoretical predictions for B parallel, 100, and B parallel, 110. For B parallel, 001, there's a discrepancy between experiment and theory regarding the phase I boundary, which is discussed in detail. The elastic constants calculations are also in quantitative agreement with the experimental ultrasound results for B parallel, 100, and B parallel, 110. However, for B parallel, 001, the calculation predicts phase 3 only at finite temperatures, whereas the experiment detects 3 phase transitions. The ultrasound results suggest that the phase transitions at B, 001, C1 and B, 001, C2 correspond to the 4 and I transitions, respectively. The hardening of the C66 mode in the phase 3 might be due to crystal deformation. The research highlights the importance of considering magneto-elastic coupling and the need for refined exchange parameters in the theoretical model for better agreement with experimental results. Here is the combined summary of pages 9 and 10 of the research paper. The authors present high-field results on SRT-CPO using ultrasound, dielectric, and magnetocaloric-effect measurements. New phase boundaries at B, 001, C2 and B, 100, C2 are discovered, which have not been detected by magnetization measurements. Theoretical calculations using the cluster mean field, CMF, method are employed to understand the origin of these phases. By considering the chiral twist effect of the cupolas, the BT phase diagram is reasonably well reproduced for 3 magnetic field directions. The assignments of the field-induced phases are carefully done by comparing the entropy and elastic response obtained by experiments and calculations. The authors propose that the phase between B, 001, C1b, 001, C2 is the phase 3 predicted by the CMF theory, based on the drastic response of the C66 mode. The reasonable agreement between experiment and theory indicates that the CMF theory well captures the nature of this quantum spin system, where competing exchange interactions and chirality play an important role in the emergence of the rich phase diagram. Figure 8 shows contour plots of the theoretically calculated magnetic entropy for different magnetic field directions, while Figure 9 displays the second derivatives of the magnetic energy with respect to strain as a function of the magnetic field. The derivatives are taken at t equals 0 for different strains, and the results are compared with experimental data. The authors acknowledge the support of various research institutions and funding agencies, and provide a comprehensive list of references. The paper concludes with a discussion of the implications of the results and potential avenues for future research. In Figure 10, the second derivatives of the magnetic energy near the phase I boundary are shown, which provides further insight into the phase transitions in SRT-CPO. The authors highlight the importance of considering magneto-elastic coupling in the model Hamiltonian to improve the agreement between experiment and theory. The research paper discusses the stability of the high-field phase in SRT-CPO under various magnetic field orientations and temperatures. It begins by explaining how changes in the twist angle can significantly influence stability, highlighting the importance of precise control. The authors then present a range of spin configurations obtained using the CMF theory, including the chiral-twist effect, to demonstrate the complex magnetic behavior. These configurations are shown in Figure 11, featuring various field and temperature parameters. The study emphasizes the importance of considering both the magnetic field orientation and temperature to understand the stability of the high-field phase. The paper concludes by highlighting the need for further research into the magnetic properties of SRTC-PO and related materials.